Hello and welcome back to Fluid 2000. This is lesson 10, and this is the lab preparation for the demonstration on lab 3, which deals with directional control valves and also speed control. Okay, so what we're going to look at in this lab is the working actions of direction and speed control. What are the options with speed control? How does force and pressure affected by speed control there? Apologize for my bad English. And what is the correlation between speed and flow? So those are the things we're going to look at. So first of all, let's take a look at your directional control valve and how directional control valves are named. So right now with this one on the particular diagram, we're showing an accumulator which has a two-way directional valve. We say two-way because the fluid has two options of the directions it can go. So in the first, when it's deactivated, it has a flow through, like on the right-hand side. And when it's activated or energized, in this case, by the solenoid, it is blocked. So this is a way that when it's deactivated or probably de-energized, that the accumulator can bleed down and therefore take pressure out of the circuit for safety reasons. And the accumulator will charge when the system is running and the pump is running. So this two-way valve is either a go or no-go operation, and that's simply it. It's a two-position. And the fluid only has two options. If I come to this one, however, the fluid has three options. It's still only a two-position valve, one with it activated, of course, and one with it deactivated. In the deactivated condition, the fluid from the annular side or the rod side of that cylinder is shunted through to the tank. So it's allowed to bleed down the tank. This will allow the load to descend when it's deactivated. When I activate it, the pressure is pumped, or the fluid is pumped through the rod side of the cylinder and the load goes up. This is a three-way directional valve and not a two-way like you might think, because the fluid has three options. It can either go straight through, it can be blocked, or it can drain through from, in this case, the top left-hand side of the bottom block to the top right side of the bottom block to the bottom left side of that block when deactivated. So that gives the fluid three options. That's why it's called a three-way valve. That's one of the biggest confusing elements of naming your valves, is figuring out, well, this is a two-way valve. The fluid goes two ways. And you're right, it does, but there's three options for the fluid to have, and that's what you remember. So this one here is a four-way valve. Again, it's only two positions, but this one illustrates the fact that the fluid in this example can go in four directions, even though the valve itself only has two directions. So going from left to right, top to bottom. So in the top left-hand block, I have trouble with my left and my right all the time, by the way, just the fluid now in the activated condition, so when the solenoid is triggered, is allowed to flow from the output, from the pressure point, to the cap end of that cylinder, extending that cylinder down. The fluid on the rod or annular end of that cylinder is allowed to come through, straight through from right to left and drain back into the tank. Now going to the right-hand diagram, we see that in this case, the fluid is pressurized from the bottom block and goes from the top left of that bottom block to the bottom right of that bottom block and charges up the rod end, retracting that cylinder and pushing the load up. The cap end is allowed to drain back to the tank on the bottom block through the right-hand top passage to the left-hand bottom passage. So this is an example of basically a two-position, four-way directional valve, if you want to look at it that way. Yeah, they could have made it easier and less confusing, I agree. However, this is what we're left with. So center port conditions in three-position valves, three-position four-way in this case, because the fluid has four ways it can go, 1, 2, 3, 4. You will either have a closed center, and a closed center actuators are left in position so that any of the actuators are left in the position they're left when the fluid flow is cut off, because the fluid can neither get back to the tank or come from the pressure point, and A and B are isolated from the rest of the circuit. Since they're isolated, they will hold pressure, or they will hold the amount of force that's required. So this can be used very usefully on farm equipment and excavators, because we're going to use a joystick control back and forth to move your actuators, to move your arms for your excavator, or to lower or raise your farm implements. A tandem center allows fluid to circulate back to the tank from the pump. This allows the fluid to circulate and be filtered and stay warm if it needs to. Not only that, because the fluid is not building pressure from the pump to the tank, it will use less energy. Remember, a pump will only work as hard as it has to in order to move that fluid around. Now, a float center is used on motors, and the reason it's used on motors is it allows a slow deceleration. If I have a motor with a large load on it, the last thing I want to do is turn it to the off position and have that motor come to a screeching halt. Anything that was attached to that motor still has inertia and will more than likely rip that motor apart, or motor mounts, or something bad will happen. So we really want to have a float center on a motor circuit that has any kind of power being used to it, because we want that motor to coast to a stop. There may be an auxiliary braking system with the motor that when it's not activated, a brake is actuated through the control mechanism, but generally motors will have a float center on their three-way valve. A two-directional motor for sure. Now, an open center is similar to a tandem center. It's used on motors, and it's less power because of the fact that you don't have that closed P-port. And remember, when you don't have a closed P-port, your pressure regulating valve, your PRV, will be triggered as the pump runs and tries to pump against a dead head. Pressure will build to that point where it will drain back through the pressure relief valve, which is set for maximum allowable pressure on the circuit, which will mean that you're going to have load on your motor and it's going to consume more power. So a good way around that is the open center, as opposed to the float center with the closed P-port. Okay, so looking at this, when you're looking at your directional control valves, you have two different types. So sometimes the O-ring seals move with the spool, and those are the types that we have in our lab because we're using a lower pressure. We're using the stationary O-ring ones in our lab because they are used for lower pressure. My mistake. The O-ring seals moving with the spool are used for higher pressure systems because generally it's not just the O-ring. The O-ring is backing up a metal plug which moves with the spool. So they generally are for higher pressure systems. A stationary O-ring system is relying just on the O-ring to hold pressure. So the O-ring will distort under pressure and wear over time, so they will tend to leak more quickly than the moving O-ring seals. And a different design of rubber too. So here's an example of a spool valve that's the same type as the one we were using. The only difference between this one and the one we're using is this one has a plastic see-through body, and the ones we're using actually have a metal body, so you can't see in them. If you take a look at the two pictures and you take a look at the picture on the left-hand side, you'll see that the scallops or the passages there are centered between two O-rings. So as the fluid goes in there, it's got nowhere to go. It comes up against both O-rings, and that'll hold pressure. When I move it to the right-hand side picture, which I'm pushing the spool valve in at this point, what ends up happening is those passages straddle the O-ring, allowing the fluid to go from one side of the O-ring to the other, and that permits flow. Now, you'll see that there's really not a lot of fluid that's going through there that will activate your motor or your piston. Now, mind you, there are a lot of little fluid passages, about 10 or 12 around the diameter of that spool valve, but still, compared to the inside diameter of the conductor, it is a little bit of a pressure restriction. And remember that all of the devices that you add to a hydraulic system will actually add some parasitic load, and therefore add to the pressure required from the pump in order to do the work that is required by the circuit. So there is some cost in doing business. Just like in an electrical circuit, every connection point adds a little bit of resistance to the overall resistance of the circuit. Every connection point, spool, valve, gauge, or conductor pipe in a hydraulic system adds a little bit of friction for the fluid, and therefore robs a little bit of power and requires a little bit of more pressure increase to get over that obstruction. Right? That's the way I kind of like to think of it. Okay, so this was the original lab that came with the note package, and you will notice that if you read through the note package again, that we will be doing lifting the power unit yet again. And I thought, well, maybe you're probably a little bored about lifting the power unit, since now we know how to calculate how much it weighs and how much force is required to lift against gravity, and all of those wonderful things we've covered in the last couple of experiments. So I decided to substitute a motor in for the loaded part of the lab. You could see the stroke and speed on the cylinder with no load on it was affected by the speed control. Looking at the speed control in the bottom of the schematic diagram there, you'll notice that it does have a check valve, and it has a variable orifice there which allows me to change the speed control. The check valve is there to allow full flow in one direction and a metered flow in the other direction. So as a result of that, you are going to see a change in speed in one direction and free speed in another. So basically what ends up happening in this circuit is flow is unchecked in one direction and slowed in the other. And we saw that in the experiment. Now, or you will see it if you're watching this one first. This is what I substituted in because we haven't taken a look at a motor yet as an actuator. So I substituted in a bi-directional motor with attached load. And you saw in the video when I went through it, I didn't quite follow the lab verbatim in there. So you can just observe that and don't worry about that. There'll be some general questions, but nothing too specific with a lot of math in it. This is more of a concept. So you saw that by varying the flow, we controlled the speed of the motor to a much greater degree than we controlled the amount of power the motor generated. The system pressure had more to do with the torque or the force applied, and the speed was controlled by the flow. So this kind of proves the point that we went from pretty much minimum pressure to maximum pressure on the system, and we were still able to move the load pretty much throughout the pressure dynamic. I mean, once we cranked it down, we were able to stall the motor at a low system pressure. It became more difficult to stall the motor at a higher system pressure. But regardless of the system pressure and the amount of load, the speed was controlled only by turning the dial on the speed control mechanism or the flow controller. So that kind of proves the concept that speed and flow are related and force and pressure are related. Now, in the next experiment, we're going to get into the areas and the force applied and the multiplication of force by changing the area, right? But on this one, we're just more concerned about the concept of flow and speed. And here's the example of the bidirectional motor with the adjustable load that we used. So this is connected with a belt. It's a cogged belt. So it has really good connection. There's no slippage in this belt at all. It's very much like a timing belt that you'd see on your car. The restriction is very simple. It's just a screwed in spring return clamp, very similar to what you would see on any kind of a disc brake system on a car. And that's what provided the load. You have your speed counter, and on the left-hand side, the second wheel there, the one that doesn't have the brake on it. And that's how we calculated the speed of rotation and which direction it was turning in. So that's the idea of this lab, was just to get you familiar with the concept of what happens when you add a speed control or a flow control to a motor, and how it affects speed and how it also affects the extension and retraction of a cylinder, right? So flow control is very important for speed, and we can preset that on some systems, and in some systems we want that to be dynamic. Now this is a fixed displacement motor that we're using. So the fixed displacement motor would be better used where I have a very predictable amount of force required, and it really doesn't change much. If I have a requirement for a speed variation over a wide variety of loads, I am probably going to go with a variable displacement motor and a speed control as well. And that would allow me the increase in the area acted on by the fluid as well as the speed of the fluid. And that would give me a much more dynamic way of controlling both my load and my speed, especially in motors. Okay, so that's enough of the prep for the lab. So if you're watching this before, have a look at how changing the pressure and changing the flow had an effect directly on the motor. And we'll see you next time for cylinders in series.